What's up, everybody? Welcome back to my channel. We're going to be discussing Quilibrium, and today's topic is going to be 2-1, Quorum, and a few extra things. If you're new to the channel, welcome. Kind of surprising to see you here because this is going to get pretty deeply technical pretty fast, but for those who are coming back, welcome back. So I'm going to go ahead and get started in the same way we do every single time as we talk about the mission of Quilibrium first. The mission of Quilibrium is to secure every bit of traffic on the web, whether it's in service of other protocols, in service of the Quilibrium protocol and applications on it itself, or in service of the broader web. Now, quick disclaimer, since we're doing a multi-stream onto Twitter this time, I just want to go ahead and mention this broadcast is not a solicitation for investment in either Quilibrium Inc. or the protocol's utility token. We do not encourage or endorse speculation in the utility token of the network. All right, so we'll go ahead and set the agenda for today. Today's agenda is going to be the near-term roadmap with all the testing going on of 2.1 and Quorum, of course, and then dive into the 2.1 architecture, what the changes are, why they matter, and then finally we're going to go through the process of the regular style dev talk where we're going to be adding features to Quorum, and we're going to be doing it live. This is going to be a new protocol message type and a new application message type. So let's go ahead and get started. To start things off, we're going to talk about the near-term roadmap. So the near-term roadmap for Quilibrium is essentially the following items. We're going to be doing a Milestone 3 update. It'll be the last update to the Milestone 3 that is in progress on testnet. It's going to basically give the rest of the components a chance to be vetted out and ensure that they are performant and behaving in the way we expect. We're going to basically finish that off with a mainnet data import and dry run. A lot of protocols do this. We're no different here. And the idea is to ensure that the network properly shards out the data that exists on mainnet as is. The network maintains consensus and continues to prove over the data sets in the new sharded tree format. The next thing we're going to also be doing is testing out the S3 and KMS APIs. I know some of you saw the recent screenshot from Quorum in testing where we were vetting out the MPC wallet. This is a very important part of this, so just stay tuned for that. It's going to be a very, very interesting feature to add. With respect to Quorum updates that are coming up in the near-term roadmap, of course, the QName service, that's going to be a very important part for having decentralized identities both on the network and for Quorum itself. The public invite link, we've seen some issues around synchronization. We're going to be resolving those and getting that update out shortly. And then, of course, the MPC wallet feature, which we're going to be targeting initial compatibility with Ethereum and Solana. This is going to be also really important for onboarding DAOs. There have been a number of DAOs that have expressed interest in wanting to move away from Discord because Discord, of course, is not decentralized remotely. It also has no encryption whatsoever besides the basic HTTPS encryption, which is effectively useless. And so they're very excited to onboard, but obviously we need useful features for supporting DAOs like MPC wallets. Last but not least in the near-term roadmap is Milestone 5. This will be introducing the schema repository, which provides essentially bonded types to the network, basically whenever you deploy an application to the network, ensuring that the data is structured in such a way that it is easily referenceable, despite the fact that it is encrypted. And then, of course, the QCL runtime and compiler will be part of Milestone 5. Once we've vetted all of this out, then we'll be proceeding to deploy 2.1 to mainnet, which is obviously one of the things people are very excited about and looking forward to. Quorum sync. Quorum sync of messages is annoying. Is there going to be a fix? Yes, that actually relates to the public invite link sync issues. It also impacts private chats, but basically it's going to be both. And part of what we're going to be drilling into today actually relates to that. It's going to be the nature of how these sharded trees for data proofs will be basically leveraged in the same way on Quorum. Let me make sure I have all of the... Again, bear with me here. This is the first time I've done multi-streaming, so this is a little bit new to me. Making sure that I got the Twitter chat included as well. I'm not seeing anything, so let me make sure that's actually the case. Yep, okay, looks like it's doing what it's supposed to. All right, cool. So let's go ahead and get started by talking about the 2.1 architecture, the problems that it's going to solve, and then we'll dive into the architectural specifics. So with respect to the 2.1 architecture, it's obviously a very large lift from where we are today. The way that the network currently works is essentially one singular data shard, which is much, much larger than a data shard will be on 2.1. It is essentially the entire token application and all of the contents of it consolidated into a single network shard. This is essentially the same approach that other networks are currently doing. For example, Ethereum does not have sharding. Everything lives within Ethereum mainnet. There are L2s that are somewhat of a... the Twitter message came through. Thank you for the test. So, we're going to be walking through that in just a few moments. But anyway, the idea is that the reason why we're doing this shard-based approach is that, again, Quilibrium was very inspired by, again, this whole notion of trying to decentralize Discord in the first place. And when you look at the architecture of applications that are running at significant scale like Discord, you have obviously a shard design that's baked into the data model. But more than that, that shard basis is something that is almost used in every single large application at scale in general. And so doing this in a cryptographically secure way that is essentially in step with the typical approach used by blockchains, we're going to have to actually redesign the way sharding is done compared to the traditional data models that are used, for example, with CellaDB for Discord or all the other types of shard basis, like, for example, Uber uses quad trees. And we're actually going to be doing something a little similar to that, but I'll get into that in just a sec. The other problem that it's going to solve outside of scaling is the topic of miner consolidation. So in proof-of-work networks, like Bitcoin, for example, being the original example of this, one of the things you kind of see is this so-called race to the bottom, where you end up with essentially all of the mining power of the network converging on just a few small number of pools. The reason this happens is because of the very nature of how rewards are distributed on the network. So with Bitcoin, when you produce a new block, the Coinbase specifies a single address that is a recipient of the reward for that block. And by consequence, that means that when you have, a very small amount of hash power for the network, then your likelihood of being an individual miner of actually receiving that reward is basically nil. And in fact, the last solo miner that received a reward was just very recently, but it was essentially such an anomaly that it was somewhat of a news story in of itself. And this is because the nature of that protocol's distribution of rewards is probabilistic. In other words, the likelihood that any one node that is producing hashes at a certain rate is essentially a percentage of the overall network's hash rate in terms of likelihood of receipt of the reward. What Quilibrium is doing differently is what is called proof of meaningful work. And we already have this somewhat encoded in the basis of the 2.0 release, but the way that this works is essentially that the nodes that are on the network, proving over a single data shard in this case, are given rewards in distribution to its membership set on the ring. Unfortunately, the membership set on the ring is very competitive. And so just like traditional proof of work models, it's causing a consolidation effect where there are basically a very large concentration of miners operating on a single pool, and it is therefore dominating the current ring 0, which is the largest reward recipient for a given frame, or equivalent would be like a block on the network as it is today. So these things in mind are what we're going to be discussing as we talk about the actual architecture of 2.1 and what makes it different and how we address this topic of scaling and miner consolidation. So let's go ahead and do something that we've done many, many times through the history of these broadcasts. We are going to be jumping into Excalidraw to draw this out. So let me go ahead and switch things over with Streamlabs. Like I said, I'm not much of a big streamer type, so this is a little bit tricky for me to get it quite right. A few more seconds. Make sure I can see the stream chat. And all right, here we go. Okay, so now we have Excalidraw pulled up. Let's talk about the nature of what we're adding in 2.1 that makes things so unique. When you try to design a database, you can think of the traditional, like just a SQL database. One of the things you run into is if you have just a big monolithic database and you have millions of users that are trying to request it at the same time, you have a certain number of constraints that exist on the given database itself. One of these things is the number of connections that database can service. Another is the amount of CPU power that it has available to it. Another is the amount of RAM it has available to it to provide things like higher level caching of repeatedly accessed data. And then, of course, you have the topic of disk space itself. A lot of databases have support for things like essentially using network attached storage or using very large redundant arrays of disks on the server itself. But at the end of the day, you have intrinsic limits. And so what often happens in database design is you'll do some form of what is called sharding. And so when you create a shard in a traditional database model, one of the first things a lot of people will do in that design is they'll essentially take the data and choose some sort of shard selection pattern. And so the shard selection pattern basically works on a few simple principles. You have the very naive approach, which is, yes, there is also MongoDB. You have the very naive approach, which is essentially saying like, okay, let's say this is a database of users. You've got user 1 and their ID is 1 because you're using sequential IDs. And I don't know why that didn't copy, but there we go. And then we have like user 2, and then basically bouncing back and forth, so on and so forth. You end up on each shard of each database, and all requests get replicated to the given shard based on what the user ID is. Where this starts to get a little tricky is when you're talking about things like social networks, where in social networks you have this notion of a graph, you know, the user's follow graph, the user's interactions with posts that they make. And these interactions oftentimes are not bounded to the user ID following this pattern of being like constantly an even number or an odd number. And of course, when you start to reach the scaling limits of those particular individual shards, you end up needing to create more shards. And then you have to redesign how you're doing those shards such that you end up bucketing users based on, in this case, you know, now you have user 3. And so you're basically doing modulo arithmetic, user 1, user 2, user 3, and they each end up on each shard based on the user's ID. And this still, again, you hit scalability limits. And there's ways that you can work around it with this approach, but at the end of the day, it's a very bad approach because it's very naive and you end up bucketing a lot of content and you end up with hotspots on these databases and it doesn't work very well. And so instead, there's another model that a lot of databases today use, which is called consistent hashing. And this is this idea where instead of trying to do this simple approach of bucketing based on modulo arithmetic of a user's ID or some other attribute of the user, you instead start to do an arithmetic of the actual content of the object itself. Sometimes it's encoded as a hash immediately and implicitly. Sometimes it's like a UUID that's assigned that is deterministically derived either from the content or it's completely random in generation in the first place. And this type of approach tries to relieve the pressure of generating hotspots. But again, hotspots can still happen. For example, consider on Twitter, Kanye just came back and now this user with a lot of followers and a lot of engagement is now suddenly hitting a very hot spot on that database because now you have millions of users that are requesting it. And so you end up with these patterns of application design where you end up with higher level caches. Somebody will, for example, on top of all this, just put a giant Redis cluster in front of it so that it can cache these responses so that they can be served faster without having to hit the databases and relieving some of the pressure that builds up on these shards. But there's still a lot of contention that can happen. And so then you also end up with other unique and novel designs, which is things like, for example, the way Discord handles data sharding, they use this model of what's called a snowflake identifier, so does Twitter. And the snowflake identifier is a sequential ID, but that sequential ID is still bucketed to each individual shard. So that way you end up with this scenario that, you know, on shard 1 over here, user ID 1, user ID 2, user ID 3, except there's also a long string of data behind it, which is the timestamp, the server cluster identifier, and a few other attributes. These are all great for traditional server designs. But when you start to get into decentralized networks, you hit a different problem. Now you have to have a deterministic way of generating identifiers, but you have to have it done in such a way that you can ensure you don't run into the hotspot problem. Or if you do, it has a way of balancing out gracefully. And so this is something that starts to get into the deeper design of databases, where you start to think about how can I take, for example, like in this database model here, and I mentioned user 2 maybe posted something that turns this second shard into a very hot hotspot. when you have an event like this, you can do a couple of things. You can add more replications, so just generate a bunch more of these clones of this database in order to handle that data. But you then run into the problem that what if that second shard is starting to actually hit the limits of data on that actual disk array? Well, then you start to run into a problem of data replication. And if you want to shard this out further, in the design of like the consistent hashing or snowflake model, you have to find a way to live rebalance that cluster. And that starts to lead to its own performance issues. And so one of the things that you can do when you start to design these is actually an interesting technique that comes from the family of quad trees. So Uber, for example, is dealing with geographic data, and that geographic data has a lot of hotspots that occur naturally because obviously when you think about geographies, there are natural hotspots that arise from large population centers. And the way that you start to think about this is take a map of the world and put it into quadrants. And so when you put the world into quadrants, obviously this is the Mercator projection that we're discussing. Obviously we're not talking about a flat Earth scenario, but when you take that particular projection, there's going to be some spots that are basically empty, like oceans. And so for those areas, you basically just need one dedicated shard for that section. But when you structure this data out and put it into a tree design, you actually have this nice little side effect that trees will continue to branch out. And so when you have a large amount of data and you're putting it into the design of a tree, and let's just block this out. So think of this large block here of the entire map as essentially the root of a tree. And then those quadrants become branches of that tree. And from this design, if you end up in the scenario where, hey, I'm starting to add a lot of data under this one quadrant, you already have a natural partition of that data following that tree pattern. And so if any one of those subsets becomes too hot to handle, you end up having this rebalancing effect where instead of having a bunch of replications of this data that is just this entire block here, when you're creating these replications, you now have, for example, 4 of them. And when you hit that intrinsic limit, you now split them out. So this one now becomes responsible for this shard, this one for this shard, this one for this shard, and this one for this shard. And so, exactly, divide and conquer. And so what's really useful in the topic of cryptographic approaches is you end up with some sort of tree structure that's used to consolidate data. And if you go all the way back to the origins of cryptocurrencies in general, you of course have Bitcoin with its original approach of the Merkle tree. And a Merkle tree basically uses a hashing technique that the leaves of the tree are hashed. These leaves are either, in the Bitcoin case, they're transactions, but in Ethereum case, there's 3 different trees. It's just basically the same idea of the leaf is hashed to a known hash value. The branches are then hashed of that hash data, and then so on and so forth until it converges on a root. And then the root hash is, of course, the finalized state that is undeniably the entire collection of data represented as a single hash commitment. Now, when you prove this data, that's where things start to get a little bit interesting. When you think about the large state of such a network, for example, Ethereum is, I want to say about 250 gigabytes of data, I believe, last time I checked. That's a lot of data. And so if you want to prove any particular hash on the network, or any particular transaction on the network's inclusion in a block, you have to actually produce the sibling hashes all the way up to the tree, up until the root, in order to prove that that is valid. And that gets pretty expensive, especially if you're dealing with a traditional Merkle tree where there's only 2 branches off of every single branch. And so in Ethereum's case, I believe the number is like somewhere around 13 or 14 essentially sibling proofs that you have to provide proof. And this is 32 bytes of data, so 32 bytes times 14. It doesn't work out to that much, but it's still pretty costly. One of the things you can do, though, is instead use a different approach to design the tree in the first place. And so that's what we've essentially done. Thanks. I'm trying my best to bring this into as conventional terms as possible, but I do recognize that like some of it gets technical a little quickly. I do appreciate people telling me what they're not understanding so that I can help clarify it, but I do try my best to keep this as approachable as possible. Anyway, so when you start to look at the tree with a different approach, instead of doing this, for example, the Merkle tree approach or the Patricia Merkle tree approach that Ethereum uses, of taking a hash of the data and then taking another hash of the data, which is, like leaf 2, leaf 1, and then taking a hash of that in order to produce the next branch above. Instead, you can take this alternative route. And what this alternative route is you encode the data into the tree such that it is instead a polynomial, essentially. And so for those who took, like high school algebra or whatever, a polynomial is essentially f of x or y equals some constant times x to the third, or whatever the highest degree of the polynomial is, x to the second plus c times x, c times x to the first, and then of course d, which is the constant at the end of the polynomial. And using this type of construction, you can actually do certain types of arithmetic in the same vein, but cryptographically. So one of the things that happened very early on in Quilibrium's network, it was like April of 2 years ago at this point, which is just staggering to think how much time has passed. We essentially kicked off what's called a Powers of Tau ceremony. And what that ceremony essentially was people would contribute random entropy, which is just generating random numbers to help secure the ultimate random values that construct polynomials for us on the network. And so with that, you have essentially the values for x are effectively invisible. Like since each one person is individually contributing that entropy and randomness, you can't actually determine what the real value for x was because it's basically locked inside of a public key point value instead of a private key that is public and exposed to the world in some way. And so by consequence, you can construct polynomials using this secure reference string, is essentially what it's called, to condense all the information that exists in a given set of leaves as what's called a vector commitment. And so what you do instead is, because we have a very large polynomial that scales up to 1024 degree, in our case, we've actually done a lot of performance testing and wound it down to 64 because that proved to be the most performant. You basically get the ability to transform the data that's being committed to in these, what's called a vector commitment, to instead be these values that roll up into these essentially coefficients of the polynomial. And when you evaluate that, you end up with a point instead of doing this approach where you end up with just chained hashes. But what's really cool about that is that because you have a string of points that lead down to the given root of data, you don't need to provide all these sibling proofs that start to get pretty expensive when you're dealing with Patricia Merkle trees, for example. And instead, you can actually just provide the string of commitments all the way up to the root, and then you have essentially a verifiable proof of whatever data was in that leaf. And that becomes a lot cheaper and a lot faster. And so that's one of the changes that we put into place for Q1, and we've been testing the performance of it, and we ultimately evaluated it and refined what the parameterization of that tree was to result in essentially about 100 millisecond tree commitment times and about 100 millisecond proof times. It's pretty damn fast. And so that's really useful for actually proving any data that exists on the network. But on top of it, it also gives us a really useful mechanism for continuing to partition out the network as a particular, branch of the tree grows out. And so this basically gives us some additional metadata that surfaces through the construction of the tree so that we can know what the total state of the network is at any given time. Like I said before, when we are constructing data on the network and putting it into this tree format, we have essentially a set of known values. What those known values are is one, the given number of leaves that are allowed on a particular branch is 64. And we know that based on the height of the tree itself, we know exactly how many sets of those 64 branches that could possibly exist off of any given branch. And so mathematically, it becomes very easy for you to then take those values, multiply them together, and get the total state size of a particular shard. And why this is useful is because it flows into the way that we calculate rewards on the network. And so our approach that's called proof of meaningful work essentially dictates that the issuance of the utility token on the network is directly bounded to a few different variables, but most importantly, one of them is the total state size of the network. This also comes into effect for calculating the fees of transactions on the network. Essentially, because adding data to the network is something that reduces the emissions of tokens on the network, there has to be a counterbalance in the effect of how much you're paying in order to put that data on the network. And so essentially, the larger the data, the greater the fee, but also the more of an impact that data has at the time that it's created on the network also directly correlates to what the fee is. So the fee actually is higher at the beginning when you're putting more and more data on there in order to ensure that issuance is effectively checked and balanced against the amount of data that's being added. All right, so this is to address the scaling consideration. So this model, basically, same kind of concept that's used, like I said, by very high data flow applications like Uber and Discord. Discord does something slightly different, obviously, with the Snowflake ID, but when you try to conceptualize it into a cryptographically based data model, it ultimately ends up looking a lot like this. And so when we're talking about the other problem that we're trying to address with the nature of 2.1's architecture, the topic of minor consolidation, you start to have to think about things in terms of what the difference is with other proof-of-work-based networks. Like I said before, Bitcoin, for example, has converged on essentially 6 large mining pools that are, dominating a force on the network. It's like, what, 70 to 80%? And that's really unfortunate because it means that the overall effective decentralization of the network is kind of lost. And so in order to combat this notion of consolidation, obviously we've already seen consolidation in 2.0 because there's only one shard, but when you start to do this sharded out approach, you're actually creating distinct and unique proofs based on each individual data shard. These proofs are computationally expensive to do. And so when you have a large cluster in 2.0, for example, what they're doing is essentially taking each frame of the network, because there's only a singular data frame for a singular shard. When they are constructing a proof, the way that it works is the frame has a set of transactions inside of it, and then ultimately this output value that is a time-based proof, and so on and so forth until infinity for each individual frame. And so when you're creating a proof, you are essentially taking that output value of the frame, encoding a little bit of data that uniquely identifies the miner, and then you are submitting the proof of that so that it ends up into the next frame. And you essentially chain this on over and over again until infinity. But the problem here is that the way that rewards are distributed is based on the number of workers that are working on a given proof. And to uniquely identify those workers, those proofs, the inputs, have to have something unique about them. And the uniqueness that we have in 2.0 is basically the output of the frame. And this isn't the right order, but this helps explain it. The output of the frame concatenated with the peer ID of the worker being rewarded, concatenated with the core ID of the individual worker. And each one of these workers is building a proof on this particular data in each iteration of the proof that it generates. And so because of that, you can actually fan this out pretty quickly. And so instead of having each individual worker having to maintain its own state, having to do a whole bunch of work that's unique to the worker, all you're doing is divvying out about 516 bytes of data plus some extra stuff to construct these inputs for the proof, and that's pretty lightweight. So you can have one single master node that is relatively large and able to handle, hundreds to thousands to tens or hundreds of thousands of workers, and just delegate out those small amounts of proof inputs, and then they can send them back. And that's essentially what's happened in 2.0. The reason why this doesn't work in 2.1, and this is the most critical observation into why the proof of meaningful work model in 2.1 is effective at combating minor consolidation, is that these individual inputs that are occurring are entirely different. And in order to maintain those proofs, you actually have to maintain that data individually on those shards in a unique way. And that's a lot more work that each individual worker has to do and requires a lot more bandwidth than the initial input data model that's happening with 2.0. And so in order to do that, let's talk about the structure of the data itself that's packed into these trees and how a given miner is operating on it. So this is the world state tree, very obviously simplified model, but this is essentially the world state tree for a given application. And so the nature of the network works like this. When you have an application, that application is essentially, the identifier is essentially unique to it, and the uniqueness of that identifier is then hashed. You take those hash values to produce what is effectively a Bloom filter selection. If you're unfamiliar with Bloom filters, like I said, this is going to be a very information-dense stream. We're going to keep the recording so people can rewatch it at their leisure, stop and rewind, learn about these concepts, and make it easier to follow along. But essentially a Bloom filter works like this. You take a certain size, usually it's much larger than this visual depiction here, but you take a bit string of a certain size, so zeros and ones, and then you take a input value, in this case this is the application identifier, and then you pass it through a series of hash functions, or if it's a one hash Bloom filter like we're using, you have multiple evaluative outputs of it. And what it essentially does is it's this, we'll just use a simple term of f of x, where x is the input, and you get this vector of outputs that is telling you which bits are selected. And so from that output, you end up picking 0, 4, and 7. And so the resulting output here is this bit string. And from that, you're basically able to dictate at a global level which shard, like global shard, is being operated on. And at the global shard level, we have essentially a construction that's combinatorial in nature. If you're familiar with combinatorics, this is one of the simplest kind. There's no special arithmetic happening here. We're essentially taking 256 possible bits and selecting 3 of them. And that selection is guaranteed, so instead of like where the possibility of a Bloom filter could traditionally pick just 1 or 2 when given the option of picking 3, we actually always guarantee that 3 are picked. So it's a unique factor of our one hash Bloom filter model. But anyway, once you evaluate this, this essentially tells you which global shards the application lives on. And then from that, those individual shards are encoded using what's called Reed-Solomon encoding in order to ensure that at least 3 individual global sections of the network are replicating this data, along with whatever other applications happen to fall in any of those given buckets for that particular application. It's the position of that placement on the vector that essentially dictates, from the Reed-Solomon encoding, which chunk of the data that it's supposed to hold. And so with that, you end up with about I can never remember the number, I always have to calculate it live, but it's essentially about 2.5 million different global shards. And that's where the network is effectively starting from the 2.0 to 2.1 transition state, is about 2.5 million global shards. And this is very fast. You can evaluate this very quickly, and nodes are essentially choosing which parts of the global shards they wish to address. Every single node by default is effectively going to be covering the token application because that matters towards every single miner. But there's also going to be other applications, for example, like Quorum, that have its own unique address space and have its own position on the Bloom filter, and nodes can choose whether or not they wish to replicate that data or not. but obviously the network is incentivized for nodes to do that. So from this level, you now have a essential position selector of where data goes. And then from there, you have an application tree that is essentially dictating how the data falls on the network. And these application trees are essentially constructed of two sets of values. If you've heard previous streams, you've heard me talk about the oblivious hypergraph, which is an oblivious data structure the network maintains in order to do querying in a secure way that provides deniability to what the user is querying, such that whatever you're querying does not reveal yourself on the network. It's one of the problems that we're addressing as part of like some of the centralizing factors of other networks. So for example, when you use Ethereum, you're using the public RPCs of Infura or Alchemy or whatever. And when you do that, you're actually revealing to Infura and Alchemy, okay, these are the addresses that I personally hold the keys to. My IP address is associated with them now. And yes, that data is used. And also all the balances thereof, all the transactions that I've done, any transaction that I'm proposing, all of that gets communicated to these centralized RPCs. And so on Quilibrium, instead, what we did is in the event that there is somebody who is providing like a large public RPC for any reason, the inputs that are being queried are effectively private, such that the RPC would not be able to determine what those inputs are. So when a user is saying, I have a token on the network, or I have a collection of tokens on the network, and I wish to query my balance of it, when I do this evaluative query, I'm actually traversing the tree in such a way that the query evaluator is blind to it. So when the hypergraph information is effectively put onto this tree, the data is constructed in two places. You have the application tree, which is essentially saying, okay, this application has shards of data that correspond to individual, whatever the constructed unit of data that's stored on the network for that application, essentially what the addresses are. So it's like little pockets of addresses. And then from there, that pocket of addresses has its own unique data tree. And the data tree is the same kind of construct. It's also the same vector commitment tree, or Verkle tree if you're familiar with that term. And that is broken down into 64-byte segments of data until you reach the final limit of whatever that data was, up to 1 gigabyte. And so each data shard can be anywhere from 64 bytes to 1 gigabyte, effectively in 64-byte chunks. And so when you're trying to calculate proofs on this, and why this comes back around to the topic of minor consolidation not being a very effective thing to do on 2.1, these breakdowns of data have to be proven to the network in order for the prover to receive its reward. And so there's a lot of different data, there's a lot of different trees, and each tree has an individual proof that has to be submitted at every interval by each prover. In order to actually maintain that, we have another topic to consider. So let's say that I am running a miner, and I want to basically Sybil squat a particular data shard that is proving to be very, it's giving me a lot of rewards, I'll put it that way. So when you have that, you have this scenario where if I wanted to, I could pretend to be 3 different nodes and then give proofs for each and every one of those trees that I have, because really I only just have 1 tree and I'm pretending to have 3. And so the way that we combat that is a technique using what's called verifiable encryption. So the network, of course, itself, this data that's being put onto the hypergraph is itself encrypted. So, holding this data, you don't know what this data is. You might have an idea based on it being a given application, but you don't know what the data is. And so when you're producing proofs on that, you're obviously having to select, chunks of data for something that you don't know what it is. But the kicker is there's still bits of data that incorporate that given verifiable encryption payload. And so you could do the naive approach where you just basically have the network issue an interval and say, based on this interval, you're going to randomly select one branch of the tree, choose that particular chunk of data, produce a time proof over it, and then output whatever that string is. But like I said, you end up with this problem where you could just basically pretend to be multiple nodes and produce the same proof, and then they would all be rewarded the same. So instead what we do is we do a second layer of verifiable encryption, so that each individual worker has to maintain a verifiably encrypted storage of that particular set of data, and it has to be unique for every single proof. And so what that means is you amplify the cost so that each one of these 3 provers whether they're real or not, would have to maintain 3 times the data stored in order to actually produce the verifiable proof of that data being encrypted of the original verifiable encrypted proof. And then on top of it, you have to still construct the particular tree-based proof in order to uniquely identify your worker and prove that you've done the right job. That's a lot of things for one worker to fake out, and in fact is something that one worker cannot fake out. You would have to create multiple workers to do it, so congratulations. If you decide to squat a particular shard, you're effectively securing the network, which means that the whole purpose of you trying to consolidate miners is kind of moot. The other thing is that this network does try to encourage replication across different jurisdictions and different IP addresses. So that way it creates this enforcing effect that allows data to be more broadly distributed. So all of these things combined effectively eliminate the miner consolidation problem. Okay, so we've talked about the shard tree structure. The other topic at hand is difficulty calibration. Like I said before, this 2-1 model has essentially workers being much more divvied out than a shrunken and consolidated model where everyone's working on the same shard. These proofs, like I said before, also have a time-based component. We utilize a verifiable delay function in order to prove that over the course of that period of time that the individual worker in question has held on to that data, because otherwise they would not be able to produce that time proof. And we continue to chain that to prove over a longer series of time that that data has been held for a certain period of time. And so by consequence, there is this issue where each individual worker is of course unique. And each individual hardware, like the server that these workers are running on, is also unique. And what we've seen with 2.0 as a very blatant demonstration of this is not all hardware is created equal. And in order to produce a verifiable delay function proof on 2.0, you have to use the same difficulty that the network is producing frames at, which is currently a difficulty of 160,000. It's essentially 160,000 steps of this VDF's iterative function. And so in this approach with 2.1, since each shard is actually just a subset, or I mean, you can use the term committee, I don't like it, but essentially a subset of workers, these workers all have, different hardware, but at the same time, maybe drastically different than the rest of the network. For example, if somebody wants to provide a lot of data storage to the network, if they're running on something like a Raspberry Pi, they will never be able to compete in order to issue VDFs at potentially the broadest level of the network at the global level. And so that would basically make a Raspberry Pi ineffective for being a worker node. So instead, each individual shard has its own calibration of difficulty. And so what we do there is we essentially take, very similar to the Bitcoin model, where at the global level, because there's only one effective shard of the network for Bitcoin, where every so often a window of time of produced proofs on the network, the difficulty is recalibrated, so too is the difficulty recalibrated on each individual shard of Q. And this data, of course, is captured in the application state tree that is rolled up to the data shards that is rolled up to the global level shards. And so by consequence, we have a bird's eye view at the global level of what the average difficulty of the network is, but also what each individual shard's difficulty is. And this is useful for two things. At the shard level, it essentially sets the pulse rate of the network. Obviously, we are targeting a 10-second time frame for each individual frame produced on each individual data shard. So if you have a cluster of Raspberry Pis and they're all mostly occupying individual frames or individual shards, those frames will probably have a lower difficulty than somebody running like a very high-end Threadripper cluster. But those Threadripper clusters may be working on something that's more unique and more valuable for that particular cluster instead of just a high data application. And so by consequence, you can have these little pockets that are much lower in difficulty than some of the other ones which are dealing with very intensive computation. And so this gives a very nice rebalancing effect where the network will essentially converge into its most useful pockets based on the nature of what those particular nodes can actually handle. So, highly data-intensive applications that don't do a lot of processing end up getting captured by Raspberry Pis. Highly data-intensive processing applications end up getting captured by potentially, Threadrippers or GPUs even, in the event that there's actually something a GPU can do very effectively. So, from this basis, we now have a series of inputs that go up through the trees and are evaluated at the public level so that we know what the average difficulty of the network is. And this is the final piece that factors into the equation of proof of meaningful work. Because we know what the average difficulty is of all of the given shards, so for the global state of the network, this average difficulty informs us what generation of the network we're currently in. So while Moore's law has been something that's been kind of contentious, like people feel like Moore's law is essentially falling apart at this point because transistors can only get so much smaller, we are still seeing improvements, either in overall speed or at least overall 3D structuring of transistors on layouts of CPU dies. And by consequence, we're still continuing to see the continued progress of computational power. So for the VDF is essentially a measurement of that for us. We are basically taking a live snapshot at every given frame, how fast the network is able to process this VDF. And because the VDF is not parallelizable, it has to be iterated in sequence. This really gives us a nice view of how fast the network is able to compute things. And because this is essentially an average, we can use this information to dictate where we are in terms of the network's generation. So the generation of a network in Quilibrium's context is essentially how fast we are in terms of exponential growth from the initial difficulty value of the network, which goes all the way back to the beginning of the launch of the network. When we launched, our VDF was quite slow. And so our iterations was about, I want to say 10,000 iterations, and we're now up to 160,000 iterations, and that's not 10 seconds though. It depends on the hardware, but that's not 10 seconds. So once we start to reach a certain point, I believe the next step is 100 million iterations, then we unlock the next generation of token issuance. Why this happens, and this is about 8 years from now, but why this happens is because one of the other consolidating effects you see of Bitcoin is that as the amount of power required in order to provide proofs becomes computationally harder and harder and harder, and there's already the friction in place of these mining pools accumulating more and more nodes, you end up with this phenomenon where, because of that consolidating pressure, you end up getting very fewer and fewer rewards, and it becomes less useful for somebody wanting to actually contribute more power to the network. And so we're starting to see a lot of arguments around what's called the security budget of Bitcoin. And so by consequence, in order to address those concerns, we have generational issuance changes to the curve. So once we've reached the next generation step, the curve rebounds such that it's able to issue more tokens so that it encourages more and more computational power and storage to continue to join to the network and not feel like it's being wastefully spent on trying to get the last few bits of quill that come out of a bounded curve that stays capped. And so that's essentially the bird's eye view and architectural details that makes 2.1 unique and also makes the proof of meaningful work algorithm work to the extent that we're trying to achieve. Okay. So I think that wraps everything up for 2.1. I'm going to go ahead and dive into the topic of building features on Quorum. If anybody's got any additional questions, I'm happy to answer them as they come up. I do have the X live feed and the Twitch live feed coming through on 2 different screens. It's a lot to juggle, but I'm trying my best here. So I have Quorum here, and Quorum, this is essentially a demonstration space. Quorum, as many of you have seen, is a alternative to Discord. It's got a very similar UI. Obviously, when you are typing things and sending things, it feels very much like the normal Discord experience, reactions, etc. The application is entirely, however, open source and encrypted end-to-end. So when you clone the Quorum desktop repository, it's actually the web application, but also has a Electron wrapper for it so that you can run it locally on your machine. You'll find obviously a very large code base, but you'll find the structure of it for the React-based application follows relatively common norms for how React-based applications are designed. And so we're going to do 2 different things here for tonight's stream. The first thing we're going to do is we're going to go ahead and augment messages so that we can add a new type of message. So what I'm going to do is I'm going to go down to the actual message mapping side of things where we basically fork off of each type of message. And by the way, for people who are wanting to contribute to the code base, this is a place where we could definitely use some refactoring because the message component has grown quite large and unwieldy. So this would be something that would be a good target for refactoring. But when you're adding a type, you essentially choose the type based on its stringified name. And then based on that, you choose how it is rendered. So for example, right now, there's only two types that we're supporting. One is text, and the other is an embed. Okay, how does it save messages for an account? So yeah, the way Quorum works is essentially each client is saving those messages. So for example, if you use Signal, this will feel very, very at home. Signal does basically it's a blind broker. When you send a message to it, it dispatches it to the relevant inboxes in such a way that it doesn't know who the sender is. And very similarly, we don't know who the sender is of a given message on Quorum either. And so those get bucketed into the appropriate inboxes. And then when a user comes online, they will fetch from those inboxes, decrypt it, and store it locally on, in this case, on their browser, on mobile and desktop, on whatever the local storage is for mobile or desktop as relevant. And you can actually see where this is happening yourself on the, where'd it go? On the MessageDB component. The MessageDB provider has all of the implementations. We'll actually dive deeper into this one because when we support new protocol message types, this is what we're going to be tacking onto. Okay, so let's go ahead and add a new type. Let's add stickers. So right now, there is no type for that, so we'll have to actually edit the given set of message types that exist. So when I get up here, you can see the collection of different content types that exist. We're going to add a sticker message. I'm going to go ahead and copy the reaction message type because it's very similar. And each one gives a unique type ID so that it makes it easy to break down the discriminated union of the combined type. And then sticker ID, and then that's basically all we need. Let me make sure that I'm not missing something. Oh, yeah. We need the replies to message ID as an optional. Okay, and that's basically it. And so now we have this message type created, and then we're going to have a unique rendering of it. It's essentially the same thing as our existing embedded image approach. So let's go ahead and take that. We don't need the outside wrapper. What we do need is the, not reactions, the stickers object. And then we'll actually filter it down to the sticker ID and provide an image URL. This is not defined, so we'll have to add it. And it essentially follows the same thing as our custom emoji approach. So, and those are always custom, so I'll just call it stickers. And then we have to modify our message props to add that as well. Oh, actually I already created that, my bad. I actually don't even need that because this is already bounded. Okay, so let me go ahead and add that, get the reference in, and then we will support that. So because this is an optional type, it's not going to create any issues in validation. Let me check this real quick. And we need to change this. This isn't going to be an array. This is going to be a map. You can tell that I've been operating in a bunch of different languages because I have a bad tendency to flip around types and values. Okay, so we have that. Now we have that, and then it does not exist on type string. This is weird. Why is it still doing that? It is the right one. Let me make sure that this isn't just the TypeScript compiler being weird. Yes, sync loops are a known issue. They are being fixed. That'll be in the next update for Quorum. Oh, that's super weird. Okay, so now it... What the... Oh, right. That's why it's getting all screwy. Okay. Cool. Okay, now we have what we needed. All right, so now we have our sticker put in place. It'll render it when we provide it. So now the next thing we need to do is provide a way to add stickers to a space, and then from there add a means to post said stickers. So the next thing we'll do is we'll go to the space editor, which is where these particularly configurable values exist. And I'm going to copy the emojis payload because it's essentially the same thing, just in a different context. You can see that I already had some of this preloaded. The whole cookbook effect. And we're going to have a separate set of root props and input props for our drop zone. And the rest remains the same. Okay. So we'll need to add the new drop zone for it. Okay. And then I'll have the same thing for this here. And then finally we will, oh, we already passed it in before. Okay, so no more work that needs to be done there. All right, so let's go ahead and, wait, I see that there's an error here. Let's make sure that this isn't something, oh, okay, that's minor. All right, so now we have this. We have our demo space. Let's edit the space. Oh, right, we need to expose it. So we have this button to set our category to emojis. We'll do the same here for stickers. Now we have stickers. Now we have our custom stickers support. Let me actually pop this window out because I do not want it to just like pop open my file browser on mainstream. It just seems like a bad idea. All right. Okay, I'll select a file. And let's see. Didn't pop open. What happened? Let's find out. So we had a upload that didn't propagate. Why didn't it propagate? Some sort of state here is not being appropriately set. So let's check. Oh, right. Okay, so this falls into the other problem I previously discussed about like certain errors not showing up like they should. That was actually just too big of a file. Let me pick a different file. Okay. Nope, that still failed. Okay, so we're going to look into why. Not getting a warning or an error about this, so that's very interesting. So we set the stickers. This happens on file upload, so my guess is something about the uploaded file is not being appropriately set. Oh, yeah, right there, duh. Set emojis. Okay, let's fix that. Okay, we'll save that, and there we go. Okay, so now it's showing up. All right, so now we have a sticker that is put in place, and we can save that. Great, now we've saved it. How do we actually surface it? So now we got to add the ability to send a message that is a sticker. And that would be under the channel itself because the editor component is there. So by the way, I'm not a React master. Like I do okay with it, but I'm not like super great at it. So if somebody wants to refactor this, please do. Okay, so we have a button here, and this is what I'm actually going to want to copy. Yeah, more components. That's literally what we need. Okay, and then I'm going to go ahead and push this over, I guess, by 12. Well, we'll definitely fix it if it's wrong, but in this case, I'm going to just go ahead and submit the message as is for the sake of simply demonstrating how it works. Okay, and so in here we'll submit the channel message, and this is going to be, let me make sure that we have the appropriate, should just be, yeah, okay, it's checking to see if it's on. Okay, cool. So here we're going to set this to sticker message. And this will be the current pass, whoops, current, do I not have it that way? Oh, user. Okay, sender ID, the, what are the properties I'm missing? Type sticker, sticker ID, Do we have the space in place? And then, what's the last component? Replies to message ID. We'll just omit that for now. Okay, cool. So now we have this in place to send a message. And then we need some kind of icon. And we just use Font Awesome. We will likely eventually have our own icon set, but we just use Font Awesome for now. Let's do smile. Okay, now we have this in place. That's not centered. Let's fix that. Also, I always struggle with Tailwind because I forget which one's which. Like, what's the... There we go. Okay, it's now centered. All right, so you can see, actually, yeah, you can see on the broadcast. You can see this button. I hit this, it'll pick the first and send it. If it actually exists. Let's make sure that that actually is the case. Oh, I still have an if there. Let's get rid of that. I don't have a pending message. There's no point to do that. Okay, now let's try it. Okay, so now we have an error of an invalid message type, and that is on MessageDB. So now we'll go over to MessageDB, and this is the second half of what I was talking about, where we support different types. So let's go ahead and look at submit channel message. Look at the pending message object. We have canonicalize, which checks to see these specific types. We'll add sticker message, and then we need to actually handle that sticker message. And once we've done that, we have basically everything we need. So oh, we don't need that because that actually gets incorporated for everyone. Sticker ID. Okay, and for this, we will consolidate into this if it doesn't exist. All right, QM, QN, and Win2O are all the icons we need. Oh, and Win2.1. Yeah, probably. Those would be fun icons to add. Okay, so now we have that. And let me make sure that there's, oh, right. So this is the other side, handling protocol messages. We're not just canonicalizing, we also have to actually handle them directly. So in the process of adding a message to a given channel, it's all the way up here, handle new message. We then invoke add message and save message. Save message puts it in the DB, add message puts it in the memory cache. Okay. So once we do that, we have handlers for the specific type of message. In this case, we can't deal with the defaults. So we will have to, man, where did that go? Actually, no, we can deal with the default because that type doesn't have anything special to handle about it. So let's go ahead and do that. We'll just let it handle the default case. But if you did have a message type that needs to be explicitly handled, this is where you would change it. Okay, now let's save the message. Okay, so it didn't render. Now we need to figure out why it didn't render. Oh, very simple. Do we have, oh, this is not the right one. Do we have this value? So let's take the, let's go ahead and just log it out to see what it says. Actually, let's log the entire stickers object. And it says undefined. Ah, that's the reason. Okay, so it's simply because we didn't pass it in. That's simple. So we'll go to channel, actually no, we'll go to message list, and then under the message object, we need the stickers. And that doesn't exist yet, so we need to pass it through. And then from there, we go to the channel. And wherever that message list component is. I literally just passed by it, yeah. And the last thing is we also need to make it optional. Okay. So now here we will have stickers and then space stickers. But we can't actually do that directly. What we need to do is we need to have a memoized component or a memoized function to evaluate the stickers so that it creates a key value mapping. All right, now we have assigned the stickers, and there it is. And that's all it takes. And so now this button should just start posting stickers mercilessly. And so we need a component to actually select it out so that it's a fully fleshed feature, but that's how easy it is to add features to Quorum. And the moment that's rolled out, that's supported on any refreshed browser or updated desktop or mobile application. So this is something that's also going to be a very valuable factor for teams that want to have specialized features. If there's something that your space wants to do that isn't in mainline Quorum, Quorum is open source. You can fork it, and then you can run it on your own individualized basis. And of course, if you'd like to, please submit a PR back. And that's basically the gist of how this works. And this is kind of one of the powerful things about Quilibrium's overall architecture is these things start to actually become surfaced in ways that compose naturally. So when you have an application and a new feature gets added to Quilibrium, you can potentially supercharge that application. One of the examples that we posted about the other day was the fact that we have MPC wallet capabilities because of our KMS service that's going to be launching in a couple days. That KMS service can be used by anybody, whether it's a wallet as a service provider or Quorum itself to embed a wallet for DAOs to operate such that they can manage funds in a jointly controlled fashion in a group chat. That's a very powerful thing. So that basically wraps everything up. I would like to revisit real quick. This broadcast is not a solicitation for investment either in Quilibrium Inc. or the protocol's utility token. We do not endorse or encourage speculation in the utility token. But thank you all for watching, and I will see you all on the next one. Catch you later.